Okay, so let's start. People will probably keep joining. So our first talk of today is by Professor Joel Drop from Caltech. It's a sort of the odd time for him to be giving the talk. It's like late evening there. So Professor Trop is a SIAM and IEEE fellow. He has been a U.S. presidential early career award recipient, and I'm pretty sure many of you have seen his papers. In particular, he's known for especially on work for concentration on matrix on for non-commutative in the non-commutative setting, and also for making them user friendly. So, and today he is going to tell us about hopefully user friendly bounds for random products rather than random sums. So,
Thank you for the kind introduction, Piyush. I know Piyush from when he spent some time at Caltech, and I see a few other people I know. Hello, Kavita. Hello, Nitesh. And I hope that one day I'll have a chance to meet more of you. All right. So today's talk is about products of random matrices and application to quantum simulation. So the approach we're going to take is very naive and very simple, but nevertheless is adequate to produce some interesting results in the application that I'll be talking about. Before we get started, I would like to say a word in memory of Elizabeth Mekas. She was a wonderful probabilist that we unexpectedly lost recently. She has a beautiful book called The Random Matrix Theory of the Classical Compact Groups, which was published by Cambridge University Press last year. And I encourage you to have a look at this. She is also well known for her research on multivariate central limit theorems and other work on hard distributed random matrices, among many other things. I think that she would have enjoyed this talk, and it's really a tremendous loss to our community. So today's talk is based on two papers, which I've written down here. The first one is about random products. That's joint with De Huang, Jonathan Niles-Weed, and Rachel Ward. The second one is about the quantum simulation application, and that paper is joint with Qifan Chung, Richard Kung, and Xinyan Wang. So the talk is going to be divided roughly into three pieces. I'm going to talk a little bit about products of random matrices, the kind of questions you might ask and where they come from. Then we'll talk about a very simple approach to studying products using martingales and the geometry of matrix spaces. And then afterward, I'll outline how this applies to a quantum simulation problem. The quantum simulation problem will be all mathematics and no quantum information, because I can't present a credible explanation of that subject. So you don't need to know anything about that to appreciate the last part of the talk. Okay, so let's get started. So the first thing I'd like to talk about is products of random matrices. So let me tell you about the model that we're going to be working with. So we're going to let Y, J, be a D by D complex random matrix. The Yj are going to be statistically independent from each other. And for simplicity, I'm just going to assume that they're all bounded. This is not very important. It's often going to be the case that these random matrices that we're going to multiply together in just a moment take the form of the identity plus a small perturbation xj. So the identity part is not random, and the xj is a perturbation of the identity. And this is a special form that comes up quite often. Now, we're going to form the product of these factors. So Zn is the product Yn, Yn minus 1, all the way down to Y1, which is, again, a random matrix that's D by D. And we'd like to understand the way that this random product evolves as the number of matrices increases. But the questions we're going to ask are not the classical ones, perhaps. They're going to be more non-asymptotic in spirit. So for a norm on matrices, we might like to ask the question about how the product grows. So in other words, what is the expectation of the size of Zn as a function of n and a function of the distributions of the factors yj? So these yj don't need to have the same distribution, and in fact, they could be quite complicated. And so the goal when studying the growth of the product is just to get a rough estimate for the order, to try and understand about how big it is in this distinguished norm. The second question you might ask about, which is the one that I'm going to focus on, is concentration. So we might also be interested in understanding how close the random matrix Zn is to its expectation as a random matrix. Now remember, with a matrix that is random, you can just take expectations of the entries individually to compute the expectation of the matrix. This is nothing fancy here. And because expectation is linear, you should keep in mind that the expectation of the product Zn is simply the product of the expectations of the individual factors, because we're assuming that everything's independent here. Okay. So these are questions that we might like to address. And in the case of concentration, it's usually enough just to get an upper bound that describes how far the product deviates from its typical value. So these are questions that we're going to ask. And these are more modern questions. I'll explain a little bit why I'm asking these questions. And they're different in spirit from the kinds of questions that people have asked in the past when they've studied these problems. Okay. Good. So where do these problems come from? Originally, they came up in the study of stochastic dynamical systems, which is an object of study in ergodic theory, control and related fields. So the idea is you've got an evolution that's maybe driven by white noise, or where the steps are not always determined completely, but actually have some distribution. And in this case, most of the work that people have done is on understanding limiting behavior. And so in this case, most of the time, the dimension D of the matrices is fixed, and the number of factors n goes off to infinity. People also study products in pure random matrix theory. And this comes up in high dimensional statistics and free probability, for example. And in this case, it's often the situation that the number of factors n is fixed, maybe just one or two even, sorry, just two or three or something like that. But in this case, people usually take the dimension d off to infinity. Now, it's recently been of interest to study iterative, randomized algorithms for solving a variety of computational problems. And so these are things like stochastic gradient, or Oja's algorithm for streaming principal component analysis, the randomized catch-marked algorithm, and other things like this. A randomized catch-marks is a randomized technique for solving overdetermined least squares problems. And so in these cases, it's often the situation that the dimension d and n are large, but not growing. So we're often interested in solving large computational problems, but the problem that you're interested in is the problem that you have to face. It's not part of some ensemble of growing problems that gets bigger and bigger. And you don't want to run the algorithm forever, so the number of iterations, n, is not going to be infinite. And so these problems call for a non-asymptotic analysis. And this gives you convergence rates. And so this is a notable difference in the way that folks in computational mathematics think about the behavior of randomized algorithms as compared with perhaps the way that folks in ergodic theory and random matrix theory have considered these problems in the past. Okay. And so it's also the case that we may want to be able to deal with matrices yi, factors that are very complicated, that don't have the same distribution, or maybe are even adapted. So each yj depends on the yj that we have already seen. All right. So these are some of the motivations for the problem that we're going to talk about. And so today, we're going to talk about a very simple geometric perspective based on martingales and geometry. And then I'll give you an application to simulation of quantum systems. Okay. If there are any basic questions, I'll stop now and ask before we move on.
No questions so far.
Great. Crystal clear. It's very hard to understand, it's hard to read the room. Okay, so part 2, products and martingales. So it's often the case that people study random products with Markov chain techniques. It's only one of a number of different ways to approach these questions. So let me remind you of what we're assuming here. We're going to be looking at a random matrix Zn, which is a product of factors yn down to y1, and the yj are d by d and independent. And so we're going to be interested in concentration. And what I'd like to observe is that the difference between this random product Zn and its expected value can certainly be written as the difference between the product of the random matrices and their expectations, because I'm assuming that everything's independent. I can pass each of the expectations onto its appropriate factor. And if you notice that you can decompose this difference in a telescoping sum. So I'm just going to write out what the telescope gives you instead of going through all the algebra here where I am guaranteed to make 200 or 300 mistakes. So the idea here is that by adding and subtracting appropriate terms, we can see this difference between the random matrices and their expectation as a sum of products where on the left side of the product, we have the expectations of random matrices we haven't looked at yet. The middle term is the deviation of yj from its mean. And then the last term is given by yj minus 1 down to y1, the product of the first j minus 1 random matrices. You should interpret this in the obvious way when j is equal to 1 or n. All right. Now, we can call these summands delta j for a reason that I will explain in just a moment. And what I want you to notice here is that by independence, conditional on y1 up to yj minus 1, delta j is 0 mean. So why is that? If you fix these random matrices here, the factor here on the left is non-random, and this extra term here is independent statistically from this tail term, this last term in the product. And so if you pass the expectation in, the expectation on yj cancels the expectation on yj here and gives you a 0. So that tells you that delta j is conditionally 0 mean given the choice of these random matrices. So what is this? Delta j is a matrix Martingale sequence. So there is nothing novel about this observation. I have seen this, for example, in one of Natesh Pillai's papers. And I imagine that it's in other places as well. But nevertheless, this is a very useful and appealing way to break down the product so that we can understand how each of the factors contributes. Now, let's start looking at the size of the deviation of Zn from its mean. So that means that we're going to need to introduce a norm. All right. So let's do that. So we're going to let norm sub p be the Shatton p norm. So remember, the Shatton p norm of a matrix is the LP norm of the singular values of the matrix. So in particular, Shatton 2 is the Frobenius norm, and Shatton infinity is the L2 operator norm. All right, let's start out with the deviation of Zn from its mean in the squared Frobenius norm. Now, remember that this is the expectation of the sum from j on 1 to n of these fluctuations, delta j squared. Now, this is a martingale in a Hilbert space because the Frobenius norm induces an inner product geometry. And therefore, by orthogonality, this is simply equal to the sum of the expectations of the delta j squared. Okay, so this is orthogonality of martingale increments in an L2 space, in an inner product space. Okay, so there's nothing fancy happening here. And we can write this out to get a better picture about what's happening. So the first term is the product of yn down to yj plus 1 under an expectation, 2 squared, operator norm squared. So I'm breaking this down. We've got a deviation term in the middle, which is going to keep the Frobenius norm on it, Shatton 2 norm. And the last term is the product of the random matrices yj down to y1. Sorry, keep getting this wrong. Operator norm squared. So this is just a matter of writing down the definition of delta j and then using the simple operator norm bound for the Frobenius norm to pull off the left factor and the right factor And then using independence, we distribute the expectation onto the deviation term here and onto the suffix term here. So the way to understand this is that we have three terms here. We've got the
This is an inequality.
Sorry, this should be less than or equal to. You're absolutely right. The first term is predicted growth times the deviation of the jth term times the expectation of zj of the norm of zj minus 1 squared. So how much has the sequence grown up to the current time? How much does the jth term fluctuate? And how much more do we predict that the sequence is going to grow in the future? And then we need to add this up over all of the summands. Okay, so this gives us a way to think about the behavior of a random product. What's already happened? How much is it fluctuating right now? And what do we anticipate is going to happen in the future? Okay, so this is very simple. Nevertheless, it's a useful way to think about this. But for many applications, especially in numerical mathematics, we don't want the Frobenius norm. We want the operator norm because it describes the action of the random product Zn on vectors. It controls the action of the product. So if you think about Zn as the iterated application of a bunch of maps to a vector, the spectral norm, the L2 operator norm, is what controls how much that random product dilates or contracts that vector. So for a lot of applications, we need a bound in the spectral norm. And for this, you need a new idea. Okay. So I see one question I can answer quickly, which is what are the conditions on the Yj? They're just D by D random matrices that are independent from each other. I'm not assuming anything else. Statistically independent random matrices. Okay? So you can think about this as an algorithm that each step makes a random choice and applies a linear map to a vector. But the linear map is chosen at random, independent of the past. Okay. Now, the idea that we're going to use is called uniform smoothness. So for a power p between 2 and infinity, uniform smoothness tells us that the expectation of the squared LP norm of a matrix Martingale sequence is bounded by a constant Cp times the sum from j equals 1 to n of the expectation of the squared LP norms of the increments of the Martingale sequence. Okay. And what is the constant? Cp is equal to p minus 1. So it's a very beautiful fact, which is actually not so easy to prove. And so this is a substitute for the orthogonality of the increments that we have in a Hilbert space, in an inner product space. So if we move to one of these norms that's not round, but is closer to being a cube, it's still smooth, but now it's puffed out a bit more. And that puffing out is visible in the appearance of this extra factor Cp. Now, this isn't really so bad because we can approximate the spectral norm by the LP norm, or sorry, by the Schatten P norm. for P about equal to the log of the dimension of the matrices. And so to remind you, the spectral norm of a matrix is always smaller than its Shatton P norm, which is always smaller than d to the 1 over p times the spectral norm. And so if we take p to be log d, this constant here is just the Euler constant E, 2.7. So forth. All right. And so with these two ideas, we can obtain spectral norm bounds for how far a random product of matrices deviates from its expected value. And a little later, I'll show you an application of this in quantum information. All right. So let me explain how this goes, and then I'll stop again to see if there are any questions on this little argument. So these ideas are very, very classical tools in Martingale theory, especially in the theory of probability in Banach spaces. And it's really no surprise that they're useful in this context. And I don't really claim any particular novelty here. Okay, so the idea is that we're going to be interested in spectral norm bounds. We're going to replace this problem by a bound in terms of the Shatton P norm, where P is equal to the log of the dimension of the matrices. Now remember that we've written this discrepancy as a Martingale sequence by uniform smoothness. We can bound this by the expectation of the squared Shatton P norms of the Martingale increments. We can bound each of these LP norms now by E, which gives us a factor of E squared, which is just a constant. We wind up with the operator norm again, and then using the same decomposition as before, we see that we need to pay for the expectation of the product from yn to yj plus 1, Shatton infinity squared, times the expected deviation of the jth term from its mean, now in Shatton infinity norm, times the expectation of the norm of the tail of, or the suffix of the sequence, the product of the first j minus 1 matrices squared. And so again, this is the same interpretation that we discussed before. The first term here is how much we anticipate that the product is going to grow in the future at time j. This term is a reflection of how much the factors yj deviate from their means. And this last term is the typical size of the random product after j minus 1 steps. Okay. And so I just wanted to give you a very simple example right now to indicate why this is interesting. So if you take each yj to be a perturbation of the identity, then yj minus its expectation is simply xj minus its expectation. And if this is indeed a perturbation of the identity, then xj and its mean are both small. So In this setting where you're multiplying together perturbations of the identity, which is one of the most common applications of this type of random matrix model in computational mathematics, you can see that each of the summands here is going to be small because the perturbations are small. And so we are taking advantage of this fact at each step. Okay, let me pause here and ask if there are questions on these ideas or how this goes. At this point, I realize there are some questions about why we should care about these problems, and I'll give you one example in a few minutes. Any questions at this stage?
It doesn't look like. So there's just one question, which is, as you said, about using these results, but nothing else. So.
All right, good. Well, I should keep moving if I want to tell you anything about quantum information. So to recap, products of random matrices are very useful for describing iterative randomized algorithms that come up in computational mathematics. These classical tools of martingale decompositions and uniform smoothness allow us to understand how much the random product deviates from its mean in the operator norm, which is a very powerful, very strong norm that controls the action of the random product on every vector. Okay, there are a lot of things you can deduce from an operator norm bound. And so what I'd like to do with the last bit of this talk is to tell you about an application to simulating a quantum evolution. This is a very important problem in a range of fields, and some people think that this is one of the most important applications, potentially, of quantum computers, which has potential applications in things like quantum chemistry, material science, the design of catalysts, pharmaceuticals, and lots of other things. We're not going to talk about any of that. I'm just going to reduce this to a math problem. So we're going to let psi in CD be a unit vector, which is also known as a quantum state, or more precisely, a pure quantum state. And you should think about D as being really big, like exponentially large, where K is the number of somehow pieces of information that are contained inside this vector. Okay. So the same way that if you've got K classical bits, they can represent 2 to the K different numbers. If you want to hold K quantum bits, you need a dimension of 2 to the K. So these vectors are very, very large in most applications. Now, we're going to let H be a D by D matrix, which is Hermitian, so conjugate symmetric, which is called a Hamiltonian. And Hamiltonians describe how quantum systems act on quantum states to make them evolve. So this is a problem in quantum dynamics. And the quantum simulation problem mathematically can be expressed as computing or approximating e to the I t h times psi, where t is a positive time parameter and I is the imaginary unit. So what we want to do here is we want to take this Hamiltonian matrix. We're going to multiply it by t and compute the complex exponential. So this matrix here is a unitary matrix, which evolves with the time t, and we want to apply that unitary matrix to this vector psi. That's all we're trying to do here. It's just a matrix vector product. But remember, psi is really, really big, and this Hamiltonian H might be really, really complicated. Now, since we're mathematicians, we're just going to set t equal to 1 from now on and not carry it around in our notation. Okay. Now, in many situations, this Hamiltonian is not just an arbitrary matrix. So a lot of the time you can write down the Hamiltonian as a sum of a very, very large number of smaller, well, not smaller, but of other Hermitian matrices, which you should think about as baby Hamiltonians. So the idea is that these baby Hamiltonians are very sparse matrices that are easy to implement with your quantum computer. So each one is like a individual quantum gate. So it does something really simple, like it switches 2 bits, qubits, or maybe it rotates 1 qubit, or something like that. It's a very, very local operation that's very, very simple to implement. And this big Hamiltonian that describes how this entire big quantum system is acting on this quantum state, on this vector, is composed of a very, very large number of these elementary operations. Okay, so you should think about L as being very large here. And I need one more piece of notation here, which should have fit on the last slide, but did not. So I'm going to add up the norms, the operator norms of these summands, and this is called the interaction strength, which is somehow a measure of how local this Hamiltonian is, how much is it making different sites interact with each other in this vector. None of this is particularly important. It's just the sort of physics gloss on all this. All right, now, the idea here is that we're going to take advantage of the structure of this Hamiltonian as a sum to try and implement it more efficiently by breaking it down into little pieces that are easy to implement. So there's an idea called a product formula that goes back to, this is usually associated with the names Lee, Trotter, and Suzuki. And their observation was that you could take this unitary matrix and represent it as a product of a bunch of little unitary matrices. I mean, of course, all unitary matrices have norm 1, but each of these unitary matrices is obtained by picking out cleverly one term from the Hamiltonian, rescaling it by a very large number, and then multiplying them together in an appropriate order. Okay. And so if we call this product here on the right Zn, the goal is to ensure that the action of the Hamiltonian for 1 unit of time is close to this product formula Zn in the infinity norm. Okay, this is what we need to happen. We want it to be smaller than some number epsilon, say. And this will ensure that this product formula, which we can implement easily by stringing together a whole bunch of little quantum gates that don't do very much, we would like this simplified approximation of the full Hamiltonian to be close in operator norm, which means that for every quantum state we apply it to, the product formula is going to give about the same outcome as the true quantum evolution. So we need to make sure that this the action of the Hamiltonian is well approximated by the product formula. So this is a very well-studied problem. And the problem is that you need n, the number of terms here, to be quite large. It should be something like the number of terms, the number of summands in the Hamiltonian times the interaction strength divided by epsilon, which has bad dependence on L, the number of summands. Okay. And so recently, people developed a new idea, which is to try and do this using randomness. And this is an idea due to Earl Campbell, I think, may go farther back than that. But the idea now is that instead of using deterministic choices of these A's, these little baby matrices, and trying to use them to build up the true unitary matrix here, we're going to choose random A's cleverly and hope that we don't need as many of them. Okay, so here's how this goes. So a random product, yes?
There's one question that the AKs don't commute, so we're not.
No, absolutely not. H is time independent here, yes. So the idea behind a random product formula is to try and write e to the th as e to the I xn divided by n times e to the I x1 divided by n, where the xi are random and simple. So you should be thinking about these random matrices xi as just choosing an appropriate aj and rescaling it. One of these summands. So some constant times al. So I'll explain how this goes in just a moment. Okay. Okay, so the idea is that instead of building up this product as a deterministic product of simple unitaries, we're going to build it up as a product of simple random unitaries and hope for the best. And so the question now is, if we want e to the IH, the true unitary we're trying to approximate to be close to Zn in spectral norm, what number n of random gates, or maybe I should just use a more mathematical term, random factors do we need? And so it turns out that for the problem that I've described to you, about the best you're going to do is log d times lambda squared divided by epsilon squared. So we've replaced the number L of terms in the sum, which I've told you is very large in a lot of interesting examples because it describes the way all of the different pieces of the Hamiltonian act on pieces of the quantum system. So we replaced L by log d, which is something like the number k of qubits, the number of pieces of information that are in this quantum state that we're operating on. And so that can be a huge reduction. On the negative side, we are now paying quadratically for the interaction strength, which is probably not good news. And we're also paying inverse quadratically for the error epsilon, which is definitely not good news if we want epsilon to be small. But nevertheless, replacing L by log D may actually be enough to counterbalance the loss here in the second term. Okay. So I've got just a few more minutes, and so I'd like to sketch quickly how this is connected with these random matrix ideas I described before. So the Q-drift protocol tells us how we're going to construct this random Hamiltonian. To approximate the true Hamiltonian. So the idea here is that we're going to draw a random matrix X that on average equals the Hamiltonian. So we can do that in the following very simple way. So we'll just pick summand AL with probability norm AL divided by the total of the norms. So this is a probability distribution. And with that probability, we'll take the L summand and rescale it in an appropriate way. So the expectation of X is actually equal to the Hamiltonian, and the norm of X is always smaller than lambda. So these things are both easy to see. Okay. Now, the idea is that we're going to construct random unitaries by taking this random matrix X and dividing it by n. Okay, so this is always a unitary matrix. And the key observation, which is not very hard to prove, but I'm not going to prove it because I'm a little short on time here. The key observation is that this approximation is pretty good. So the deviation between V and its mean is at most 2 lambda divided by the number n. So each one of these V's is pretty close to its expectation. Okay. And furthermore, V is, or the expectation of V is also a good approximation to e to the IH divided by n. And this bound is actually quite good, but I don't have it here in front of me because my notes are a mess. Okay, so each one of these V's is a pretty good approximation to a little piece of the Hamiltonian, this unitary matrix we're trying to approximate. And so we form the product Zn, which is Vn, down to V1, where the Vj are IID copies of this individual factor, V. And then the question is, how well does this product approximate the unitary matrix e to the IH, the evolution described by this Hamiltonian as a function of n? So this is what we'd like to understand. So we have presented a randomized method for building up an approximation, Zn, of the unitary matrix e to the IH, which describes the evolution of this random state under this quantum system. And we'd like to know how big n needs to be for this random product to do a good job in approximating the state. Okay. So let me just say a few more words about this to make the connection between what we were doing before. So the error in the approximation has two pieces. It's the difference between the unitary matrix given by the true Hamiltonian and the expectation of the product, which is given by this randomized algorithm, plus the expectation of the product minus the product itself in the Shatton infinity norm. This first term is controlled by a little bit of matrix analysis that I'm not going to talk about. It's not very hard. So maybe I should tell you what the bound is. So the first term is pretty small. It is lambda squared divided by n. And to bound the second term, we use the random product approach. So the second term is less than or equal to P, which is the log of the dimension of the matrix, times the sum from j equals 1 to n of the expectation of these deviations, this Martingale sequence, which is the sum from j equals 1 to n of the expectation of Vn down to Vj plus 1 times the expectation of Vj minus its mean. Sorry, these should all be infinity norms squared. And then the last term is the expectation of Vj minus 1 all the way down to V1 infinity norms squared. All right, here's the punchline. This first term here, the initial j, choices of V, is a product of unitary matrices. So what is its spectral norm? Its spectral norm is 1. What about this first term here, the predicted growth in the future? Well, by Jensen's inequality, we can pull the expectation out front, and we get a product of O, random unitary matrices, whose spectral norm always is equal to 1. Now, what's left is the deviation term, which is actually deterministically bounded by lambda squared divided by n squared by the punchline from before, which gives us the log of the dimension times lambda squared divided by n. Okay, and when you combine all this, the error in approximating the true unitary matrix e to the IH using this random product is controlled by the log of the dimension times lambda squared divided by n. And this is where we get the dependency of 1 over epsilon squared from in the bound. So to summarize, what we've seen here is that there's an elegant way to try and approximate the evolution of a quantum system using a random product of unitary matrices that are easier to implement either computationally or with a quantum computer that maybe one day will exist. And using these tools from the theory of matrix martingales and uniform smoothness, we can very easily obtain a simple bound on how well this random product formula approximates the true unitary evolution. And at least in some settings, these random product formulas are super efficient as compared with deterministic product formulas. And so they may have some potential in quantum information science. All right, that's all I wanted to tell you, and I appreciate your extra attention. Thank you. Piyush, you're muted.
See, so just a couple of questions that I had before we go to the other one. So the first error bound in the first term is just the usual Suzuki-Trotter error bound.
Yep.
Yeah. And
That's right.
should I think of it as that what is helping here is that the terms in the products are almost commuting, like there are so in this case, for example, they're all their expectation is all e to the IH over n.
I think one way to think about it is that these random products mix things faster. So because they're long-range interactions here, what can happen is that when you put in a random product term, it can move information from one place to someplace else somehow more efficiently. Whereas these deterministic formulas have to be very carefully calibrated to make everything balance out right. And somehow doing things at random just ensures that it works well on average, and that's good enough. Yeah, that's all I'm going to say about that.
Then maybe we can go over the questions in the chat. So there's one about so there are two about what is the interpretation of the products. We already have seen one in the quantum theory.
Let me answer the last question first.
Yeah.
So the question is, how do we initialize the AL? So these AL are actually part of the problem data. So the idea here is that you are given a decomposition of this Hamiltonian as a sum of ALs, and it is your job to approximate e to the IH, a unitary matrix determined by this Hermitian matrix. And one way to do that is just to take the individual summands in a careful order, scale them down, and multiply all these little unitaries together to approximate the big unitary that we care about. Another approach is to choose random terms, AL, from the sum, and then rescale them and multiply those unitaries determined by the random choices of terms from the sum. You multiply those guys together to approximate the big unitary e to the IH that we're trying to approximate. But there's not an initialization here. The decomposition of H into a sum of simple Hamiltonians is problem data that someone needs to give you. Okay. Yeah, do we want to go back up to the top? Let's see. Why is Zn an interesting quantity to study? Well, one reason is that Zn is a model for a random product formula, which is a potentially implementable approximation of a quantum evolution. So that's the answer that I'm giving you in this talk. In other settings, Zn describes the action of an iterative randomized algorithm, where at each step, the randomized algorithm chooses a randomized linear operator and applies it to a vector or several vectors, and does this over and over again. So for example, the randomized Catch-Martz algorithm for solving a overdetermined least squares problem picks an equation in the least squares problem at random, solves that equation exactly, and updates the guess for the overall solution by that amount. And then it repeats that process over and over again. That can be represented as a product of random matrices of the form identity minus a positive matrix. Okay, so that's one example. And there are a lot of other examples in the study of randomized algorithms, which is how I got interested in this. And this random product is just the quantity that turns up in that setting.
There's a next question there, which is about can we interpret these products as compositions of linear operators in deep linear neural networks?
Yep. So I know approximately nothing about neural networks. So I can't speak definitively about this. Neural networks also are nonlinear. So this is not really a very good model for a neural network. There are some people who study linearized models for neural networks, although I think that by removing the nonlinearities, you're really studying a different problem and removing something that makes neural networks effective in practice. But the second part of the question about can you make an argument that you get convergence to a random, some kind of convergence to a fixed point? That's exactly one of the classical questions that people ask about random products. So if you have a product of random contractions, for example, then you might hope that that product converges to zero in norm, in which case this random dynamical system determined by that product of contractions collapses to zero, to a stable point. And of course, you can also generalize this to understand convergence of these randomized dynamical systems to fixed points. So that's also an application of these kinds of tools. Yeah.
So there's one question by Vivek Borkar. Are there extensions to non-ID and Markov dependence settings?
Yes, absolutely. So I did not assume IID anywhere until the very last step when we started talking about quantum evolution, in which case that algorithm naturally chooses IID matrices, but there's no reason the matrices need to be IID. And so there are a lot of randomized algorithms where in fact you would like each of the, let me go back here, where you would like each of the factors yj to depend on everything that's happened so far. Okay, it should be maybe adapted so it doesn't depend on what happens in the future, but it's very often the case that randomized algorithms make choices based on hindsight. Okay, and so these methods all have extensions to those settings, which is one of the appealing things about using these kinds of martingale techniques. It's a little bit harder to prove those results. They're in the first paper that I described. And the fact is, I actually think that all of this stuff can still be refined and extended further, maybe using different sets of ideas. But somehow this is already a sufficient set of ideas to understand the random product formulas for quantum simulation, and it actually gives essentially sharp results in those settings. So, yes.
Next question is from Natesh Pillai. Is this related to embeddings, Johnson and Strauss, etc.?
Okay, so the log D is not the same logarithm that comes up in Johnson, Linden, Strauss. So this is simply to do with the fact that we're approximating the Shatton infinity norm by the Shatton P norm for P equals log D. And so you need to do that to pass from the non-smooth infinity norm to the smooth Shatton P norm so that you can invoke these uniform smoothness tools. Another way to see this is that if you've got a random matrix with independent diagonal entries, and you'd like to know what a spectral norm is, the norm of that matrix is the maximum norm of one of the diagonal entries. And if those are Gaussians, for example, you're going to get a dimensional factor that comes out just because you're taking the maximum of some independent Gaussians. Okay, so that's another reason that logarithms maybe come up naturally in this kind of setting. The 1 over epsilon squared is a feature of Monte Carlo methods generally. So when you're averaging things together, you expect this sort of 1 over root n behavior, which is exactly what we got. Of course, 1 over epsilon squared is a terrible kind of approximation bound. It makes you sad, and you would like to do better if at all possible. It turns out that there are, if you make more restrictions on what you ask from the random product formula, you can actually get better dependence on epsilon, but that's something that would be more appropriate for a quantum audience that I would be too scared to address anyway.
Next question is about can the idea of approximating a sum or product of matrices by a random sum or smaller or product generalize more broadly, and where else has this been successfully done recently?
Yeah, so I am not aware of other examples of this kind of random product formula being used for, as an empirical proxy for for something else. There are lots of settings where people use empirical approximation of sums. So for example, if you would like to approximate a combinatorial graph by a sparse combinatorial graph, one way to do that is to sample edges randomly from the graph with probabilities proportional to the conductances of the edges. And if you do so, you obtain a very sparse graph that is equivalent, whose Laplacian is equivalent to the Laplacian of the graph you started with. So that's an empirical graph approximation that is also based on random matrix tools, but it's more in the spirit of sums rather than products. These product tools mostly, I haven't seen examples of empirical approximation of products like the one that I described, which is part of the reason I wanted to show it to y'all. But there are a lot of applications in randomized algorithms where the action of the algorithm can be interpreted as a random product. And so understanding the evolution of the algorithm amounts to understanding something about a random product of matrices.
So one slightly different setting where the random products show up is this all these recent quantum supremacy experiments, for example. So there the unitaries are random. I mean, but that's a different setting where the unitary is supposed to be mostly sparse, but each individual of them is a random matrix. And then the goal is to understand the action of this on one particular vector. But it's a very, so what you're asking of it is sort of different.
I'd be interested to see that reference.
Yes, I can see. And yes, there's one more question about so the disadvantage of random products is the 1 over epsilon square term. It's not there for deterministic products. Is it possible the best of both?
That's a great question. As I was preparing this talk, I sent my collaborators an email asking them exactly this, whether there is a way to. So reducing the amount of randomness is probably not going to help in the sense that you can't de-randomize this and expect to get better behavior. But on the other hand, I think that there could be alternative algorithms that reduce the size of the thing that's fluctuating, in which case you don't care as much about the 1 over epsilon squared behavior. So this is something that is probably worth investigating. I will note that for other applications of these product formulas where you ask a bit less of the product formula, you can get a 1 over epsilon dependence in those contexts. And you can see a huge difference in simulations from that improvement. It really makes a significant difference. 1 over epsilon is great. 1 over epsilon, well, okay, it's not great. 1 over epsilon is okay. 1 over epsilon squared is pretty bad. And as a side note, the Johnson-Lindenstrauss lemma is not practically useful because of that 1 over epsilon squared. If you really want the outcome of the Johnson-Lindenstrauss lemma to hold, you typically need the embedding dimension to be huge, in part to tamp down the horrible dependence on the approximation error. And that's true even if you don't even ask the approximation error to be small. So this difference between 1 over epsilon and 1 over epsilon squared is a huge challenge in computational math. And getting the 1 over epsilon behavior is really a consummation devoutly to be wished.
Okay, I think those are all the questions so far, unless I've missed any questions. I think.
Great. Well, thank you so much for your attention so early in the morning, so early in the year. And I hope that someday I will be able to visit y'all in Bangalore.
Yeah, so let's thank Shah for answering all the questions and for the report. Okay, so our next talk is in the evening at same time, 5:30.
And Piyush, I do have the whiteboard transcript, which I can send to you.
Yes. So I think yeah. So you can send it to me, and I just share them with the ICDS, or you
That's
can also
fine.
send it directly to the.
Okay, great. Well,
So
have a good day.
so just to mention that all the talks are recorded and they're on ICTS. I think their YouTube channel, so you can also see them there. I think the link is probably on the program page, and it's also there on the Zoom. If you see this live icon at the top, and if you click on that, you get a link to the stream.
Yeah.
Okay. Okay.
Okay, great. Have a good day. Take care.